Welcome you all to this course on defects in materials. In the last two classes, we have looked at or studied the stress and strain field around screw, edge and mixed dislocations, and also because of the stress and strain field around this dislocation, what is the increase in energy which will occur in the material and which is called as the self energy of the dislocation. Okay. Then we looked at this self energy itself can be considered as equivalent to a line tension. Okay. That is because dislocation can be considered like a line which is quite taut. So that tension, how to derive an expression, how the line tension can be related if a dislocation is bent. Okay. What is the sort of stress which will be required to bend to a particular radius? These are all the aspects which we have looked at it. In the next few classes, we will look at if we apply an external stress to this dislocation, which are essentially creating internal strains and stresses within the material, what are the type of forces which will be acting on the material. Okay. What is the first thing which you should to understand the force on dislocation? Okay. Because we know that what we are generally applying to a material is when we apply a load, we always try to find out what is the stresses which are acting on different surfaces. That is the information which we have. Okay. Let us consider this case where there is no dislocation is being considered. It is on a surface, one plane which we call it as a slip plane, over which the one layer of an atom moves on top of it the other. In this particular case, okay, when a stress is being applied, okay, what are types of forces which we can have? When we apply an external stress, okay, it will be doing some work. Suppose you assume that the case where there is a dislocation is present in the material. What does this dislocation do? This dislocation, we will see that the dislocation moves from one position to another. Okay, we are seeing the image of the dislocation which is moving. That means that when the dislocation moves, we can consider that this force is essentially, or this stress is doing some work on the material. Correct? So when a dislocation is present, there is a stress and strain field around the dislocation. That we can calculate what is the energy, that is the self energy of the material. When we apply an external stress, in this direction we are applying the dislocation moves from here and reaches here. So what we will see is that as a function of position of dislocation in the sample, the self energy remains the same, it does not vary, right. Only thing what the external stress does, it makes the dislocation move from one region to another region it has moved. It is equivalent to a unit length of a dislocation. Let us consider, okay, let's sample. This length, assume that it has moved some distance dx, okay, the dislocation has moved under the action of the stress which is applied. So what is the area which it has covered? The area which will be into 1 into dx, correct? It is a unit length. This area, if you multiply it by the stress, that gives the force which is acting on that area, correct? This can be written as Vx into dx, correct? This is the stress which is force which is acting on that area of the, because stress multiplied by area gives the force acting on that. But what it has done, whenever any dislocation moves, it displaces every atomic layer by a Budges vector. That means that if it has moved from here to a position here and this distance is dx, okay, this much layer which was originally was there at some position has been displaced by a bias vector always, correct? The total moment, it was like this, each layer has moved, means that from here the next position when it has been shifted by a bias vector. So that is the displacement. So if you put that displacement into account, now we get what is the work which is being done to move the dislocation, correct? So this is a form of an energy which we get it, and the force is nothing but minus dx, which it will turn out to be, this will be sigma yx into b, it will come, correct? We have looked at the work, right? So that is what this expression which it gives is the what is the total energy, okay? Now in this we can look at it this way. Suppose we assume that across the slip line, okay, if you look at it, this is the slip line. Around this slip line, the top layer and the bottom layer is being relatively displaced, correct? What is the displacement which has taken place? Dislocation which was there initially here, it has moved to this place. Suppose we assume that on the dislocation, a force which is acting on that unit length of the dislocation, it has displaced it by this distance dx, then this force into displacement becomes the work. One will be opposite of the other, and we can equate these to dx, right? From this immediately we can get that force will be equal to sigma y into x. The sigma y into that shear stress multiplied by bias vector. But only problem in this way of looking at it, this gives a qualitative way of how to find out the force, okay? But which direction the force is acting? We don't get any information from this sort of an expression, because in this particular case which we had given it here, the bias vector is in the negative direction, okay? Then sigma xy is applied in this direction, okay? And with respect to a definition which has been used, if we substitute for the value of b, here the b is minus, because in the negative direction the force turns out to be in the positive direction, okay? This way we can find out. The situation becomes more complicated when we look at a force on a screw dislocation. What are the types of forces which can act on a screw dislocation? That is, if we consider a block, the material, where you assume that a screw dislocation is there going this block and coming out onto this surface, okay? Because the symbol which we use, if we use the same symbol for a screw and an edge dislocation, okay, we should not confuse it with it. So this is what is there in this block is a screw dislocation, okay? The coordinate system which we are using it is x, y, and z is the coordinate, positive z direction. This is the direction u of the dislocation which we take in. Okay. The stress can be applied in this direction. This will be, so on the negative side of it we will be applying it in the opposite direction. Then which is the direction in which this dislocation moves here? Actually, the expression tells that the force is equal to into B, it turns out to be. But in which direction this force is going to act on the dislocation? That doesn't become very clear. Okay? Actually, this force will be acting in the x direction. Okay? Similarly, if a stress is being applied, that is on the x surface, sigma xz, okay, the same thing will happen. But application of the external stress, looking at it, we are not able to make out what is the direction in which the force is going to be applied. That is one of the problem of this way of looking at it. Okay. I am just showing many cases where that it's not that easy. Okay. Let us take, suppose, a material which contains a screw dislocation. Instead of a screw, an edge dislocation is there. That same material where an edge dislocation is there, instead of a shear stress, we apply a tensile stress on these surfaces, tensile or a compressive stress. Then what do we naturally expect to happen to the edge dislocation? This dislocation under the action of a tensile or a compressive stress is essentially it's pulling it apart or compressing it. And edge dislocation means that having one extra plane above this slip plane, correct? Above this slip plane, we have an extra plane which is going to be there. If we apply a stress, what will happen? Tensile stress, what will happen? Then, like see this example. Here we have this one, I am just showing it. This is normally what it is there. I apply a stress, tensile stress and try to pull it. This will just go in. So the whole extra layer will move inside. So if the whole extra layer move inside, or when this is there like this, to which when I apply a compressive stress, it will be pushing this layer out and it will be finally just coming out of the surface. That's how the dislocation will vanish. That means that the dislocation, as if on the dislocation line, a force is acting which is it is making it move up or down. So now the force is acting, here the force is acting in the x direction, here the force is acting in the y direction. We will call it as Fy as the component. Okay. The application of a tensile stress or a compressive stress on the sample essentially makes the dislocation move up or down. This is what we call it as a non-conservative motion or a climb process of a dislocation. Correct? But in this, qualitatively applying a logic, we are able to try to find out in which direction the dislocation motion is taking place. But there is an elegant way in which this entire thing could be derived. Okay, that is what we will look at it. That is, we wanted to find out a force which is acting on a dislocation, okay, which is moving in any direction in the crystal, which is stressed internally or externally. Okay. If you remember, when we talked about the stress and strains, we said that there are 9 components of stress which are there, which we define with respect to a small unit cube, correct? You remember that? That is, if you take a small cube, okay, then this is how we defined x, y, z, okay. With respect to this coordinate system which we have chosen, on this face we will have sigma xx, okay. In this direction sigma xz, correct? This is how the, similarly on all the other faces are there. If we have these components which are known, okay, what will be the force which is acting on any random plane? That expression which we have derived. Suppose we assume that there is a plane which we consider it as this plane, okay, and the normal to this plane is n, okay, and the force which is acting across this plane, that is the component Fi, will be into Nj. This is the sort of expression which we have derived. If you remember that, this is nothing but writing Fx will be equal to Jx Nj, correct? Similarly, we can write an expression with respect to the normal stress which is with respect to a plane normal, okay, we can find out the components of the force acting across this plane in x, y and z direction. We have derived that formula. I am not going into that detail. Okay. So this will turn out to be, if you expand it, it will be xx into n is. Similarly for f of y, f of z, we can write similar expressions, correct? This tells what is the force which is going to act across this. Now let us assume that, take care of the slip plane, okay? Let us look at that slip plane is defined by the plane normal, correct? That is, assume that n defines the plane normal to the slip plane. And then what is the force which is going to act if we know assume that we apply a load, external load, okay, and the components of the stresses which are going to act on this are given by these terms, okay. Then we can find out what is going to be the force which is going to act on this by this expression sigma into n. This is how we write it, right, in the tensorial notation. The force which is acting, we can write it like this, whereas n will be I into nx plus j into ny plus k into nz, okay. Sigma will be essentially these terms which will come into the picture, correct, the 9 components which we know. So this gives us what is going to be the force which is going to act across the slip plane. Now we have to look at how do we define n. That is, if we know a slip plane, okay, if you know the line direction, you assume that the line direction is the direction of the dislocation. We define it as u, okay. And if the dislocation moves by a distance d in this, that is unit vector in the direction. So the cross product of it, n will be equal to u cross d, we can write it in the plane normal, because in the plane the dislocation line direction and the direction in which the dislocation moves, you take it to be unit vector in the direction, then the cross product will tell you the plane. So n can be now written as u cross d, okay, where u is a unit vector parallel to a dislocation line direction and d is a unit vector in the direction of motion of the dislocation, okay. But what we have to look at this now is that when this force is being applied, suppose it makes the dislocation move, because d is the movement of the dislocation unit vector in the direction of motion of the dislocation. When the dislocation moves, what is going to be the work which is going to be done? Is this force, okay, times the Burgess vector dot product, if we take it, that will tell you the force, because you remember that when we initially derived, okay, what is going to be the force which is acting on an area, okay, that essentially displaces that area by a Burgess vector. So if you take the dot product, then work will be sigma n, because this is not a, you should understand that when I put a dot, this is not a dot product which we use it for vectors, okay. This dot b it will come, okay. This is what the work which is going to be done. If you try to expand this one, okay, that is, this force we have already written the terms, okay. Then the b can be defined as I into generalized form, if you write it, I into bx plus j into by plus k into bz, okay. These are all the components of b in x, y and z direction, the coordinate system which we have chosen, okay. Then when we take this product, okay, that is what essentially is being shown in this slide. Now you can see that this is sigma xx into nx into bx plus sigma yx into ny into bx. These are all terms are all scalars, correct? It's only coefficients. Now this can be rearranged in a different form. Nx and bx, nx and by there. So if I write it in terms of the coefficients which correspond to nx, then I will be writing it in this form. Sigma xx into bx plus sigma xy into by. This way I can write it. If I write this way, now this will be equivalent to writing that dot b will be equal to sigma into b, okay, dot n. This just changes. Okay. So these are only some mathematical operation which we have just done. Okay. So this is equivalent to what is the work which on the plane, that is on the dislocation, what is the force which is going to act on the dislocation times, okay, the distance which it has moved. That's equivalent to it. And that force is always going to be negative. Okay. That is what essentially is being given here. Now we have written n to be equal to, okay, u cross d. If we substitute in this, so now this is a vector, correct? This is a vector. So you know the in vector algebra, scalar vector product, if you look at it, this can be written as, that is a dot b cross c can be written as a cross b dot c. These are all the same, correct? Box product. So the same thing which we do it. So then this becomes sigma b cross u, okay, dot d, we can write it. Is it not? What is d? D is a movement which has taken place in the dislocation moment direction, unit vector movement. So this can be written as equivalent to a force which is F, okay, dot d. That's also equivalent to energy. So this force now becomes equal to b cross u, right? If you look at this expression, it immediately becomes very clear that the force has to be perpendicular to these two vectors, correct? That means that if it's perpendicular to this vector, means that this is u is the line direction, that the force acting on the dislocation is always perpendicular to the line direction. This is the first point which becomes obvious from this. Okay. That means that suppose we have a dislocation which is curved like this. Okay. The force will in this direction, because this will be the line direction, and here the force will be in this direction, here the force will be in this direction, here the force will be each of this direction. You look at this, the force has to be perpendicular to the line direction. Okay. What will be the consequence of it? This has a lot of consequence, because this is a very important significant result, because this result can explain how the dislocation is going to move and expand. Okay. One of the simplest case which I will consider, suppose we assume that a dislocation is held around these 2 points. Okay. It is being pinned. Okay. Initially the dislocation is like this, and some stress is being applied. The dislocation bends like this, okay, and then the bending becomes more, and at some particular stage it becomes like equivalent to that of a semicircle. When it reaches that stage, in this particular case, this is the direction in which the force will be acting, right? This is the direction. When it reaches the case, you consider when it becomes a semicircle, how will the force act? The force will be acting here in this direction on the dislocation, but at this one, it's being pinned, the force is acting in this direction, perpendicular. So when that happens, the dislocation moves in the direction force which is acting, in that direction the dislocation is moving. So now the dislocation can try to bend around this, okay. That is what makes the dislocation form loops around precipitates, okay. This we will come later when we talk about dislocation precipitate interaction, but what I wanted you to understand is that though the stress is applied in the same direction, this is the direction in which the external stress is being applied, but the force which is acting on the dislocation because of the external stress is always perpendicular to the line direction. Because of that, this dislocation, this part may move in this direction, this part may move in this direction in the expansion, correct? So this is something which is very significant, which one should understand that. This one, sigma dot b, because here we started with respect to a plane normal, okay, the force which is acting with respect to a plane normal, and now using this mathematics we had come to this one where this is a force this equivalent to, because b is a vector, correct. So the force which is acting across a plane which is perpendicular to the Burgess vector, this force is called as the Peach-Coiler force, okay. Is this clear? Okay. So if this is clear, now what are terms which we should know about the forces which are acting on the dislocations? There are, it's a generalized expression which we have derived. If you know the components of the stress which are acting on different directions with respect to a crystallographic system which we have chosen, okay, we can find out the force which is acting across the Burgess vector direction and also the force which is acting in the slip plane on the dislocation line. We have derived that expression, okay. So essentially if you look at it, I will just write it down because I consider that this is one of the most significant because this expression will be required also further to look at various cases. Z is Z into dx, okay. This is one and this is nothing but the g equals I into gx, correct, plus j into gy plus k into gz. Then the line direction u, we write it as I into ux plus k into uy plus j into uz. Burgess vector j into by plus k into bz. These are all the things. That is, this is the way we generally represent the Burgess vector and the line direction and the Peach-Coiler force, okay. Then if this is there, the other significant expression F is equal to G cross U, okay. This is how we can find out the force which is acting on a dislocation which has a line direction U and the Burgess vector B, okay. And this F, whatever you consider, is always the force acting per unit length of the dislocation, okay. That we should always remember, okay. Let us consider some examples, okay. One is an effect of external stress on the dislocation motion, okay. We will consider it on a single dislocation. Another is, suppose dislocations are present within the material. What are the types of forces which are going to act between the dislocations when more than one dislocation is present? That is, first we consider a case when it's an effect of an external applied force on a single dislocation. Okay. This is almost what we are trying to do, is coming back to initially we started with the problem of looking at what is the direction in which the force will be acting on a dislocation. You remember the case, we consider this case, assume that the dislocation is there. Okay, suppose we choose the coordinate system Z, Y, Z, X, Y, and what is the direction? If this is the applied in this direction, what is the direction in which, okay, in this particular case Bx positive direction is the one which the bias vector is going to be there for an edge dislocation. What is the direction in which the force will be acting on this dislocation we wanted to find out. Okay, right. So what is the simplest way in which we can do this? Okay, we can do it for an edge as well as a screw dislocation. Let us first consider the screw dislocation. In the case of a screw dislocation, if we consider, the internal stresses which are generated are only in sigma yz and sigma xz direction with respect to a coordinates which we have chosen. That is, for a screw dislocation, this is the direction, positive direction of the line direction, and the bias vector is also going to be in this direction, correct? So u will become k into uz, correct? With respect to a vector notation which you have taken, the others are going to be 0 because this is a generalized direction of vector for u. Then for the bias vector, then it will become, b will become k into bz, right? Only the z component, because that expression which you have derived is for a with respect to a coordinate system, the generalized direction for u and the generalized direction for the bias vector. Okay. Now, any external stress if you try to apply and find out the components of the external stress which are going to be there, okay, then the components which external stress will have is the 9 components will be there, sigma xx, sigma yy, sigma zz, then sigma xy, sigma yz, sigma xz. All these components are of the load which you have applied in a particular direction, their components will be there along these various directions with respect to a coordinate axis, these 9 components. But which of the ones will be acting on the effect is only sigma yz and sigma xz, because that is where the displacements are. So only these components of the external stress will have any effect on the screw dislocation, others will not have any effect on the screw dislocation. Is this clear? Okay. So we will consider these cases, that if that is the case, in this expression of G which we have written here, okay, here it has to be Bz, correct. Then Kbz, correct. Now Bx and By, all these terms are 0. Now what will this Gx turns out to be? Gx will turn out to be sigma xz into Bz, correct. Gy will be equal to sigma yz into Bz. Gz will be equal to sigma zz into Bz. But this term will be equal to 0 because sigma zz will not have any effect. So only this. So now G becomes I into sigma xz into Bz plus J into sigma yz into Bz, correct. So what is the direction in which the force is going to operate? This is G cross U. So that will become Bz cross U is K into Uz, correct. finally this expression will turn out to be I cross j will be minus j cross k will be I, correct? So this will be I into sigma yz into bz into uz minus j into sigma xz into bz into uz. Okay, if u is a vector which we taken to be essentially unit vector, then uz term will be just 1, correct? Now we can find out that what does this I means. This can be written as f can be written into I into fx plus j into fy. Okay, this term equals fx, this term becomes, that is, yeah, plus I will put this as equal or yeah minus. So this with a minus sign, okay, will be minus sign, will become Fy, correct? So this tells what are the forces which are going to act on the dislocation x and y direction alone, which is going to be there. Okay, but if you try to look at what is the net force, okay, that will be, if you integrate it over all the area, it will turn out to be 0 on the dislocation. But what this is important is that this is just telling us that what will be the effect of the applied force. Now let us take that internal stresses. If you take it, okay, what is sigma yz is the stress which we are externally applying it, correct? So at any particular point with respect to a dislocation, we are trying to find out what is going to be the external stress which will be acting on it, correct? With respect to this, suppose yz we apply it, okay, that is x is in the only yz. If you are trying to apply on this, what it tells is that the force is going to act in Fx, correct? That is in the x direction the force is going to act in a screw dislocation. This is equivalent to the case of the screw dislocation which we have considered, okay. In the case of a screw dislocation which we considered earlier, okay, the stress is being applied yz in this direction and in this direction on the bottom surface yz, okay, and the u is in this direction, bias vector is also in this direction, and because this is the coordinate system which we have chosen, x, y and z. Now what we are finding is that the force is going to act in the x direction, correct? When sigma yz stress is being applied on this plane, the force is in this direction. What is going to happen? That is, suppose the stress which is being applied is sigma xz. Sigma xz means that on the x surface in the yz direction we are applying a stress, shear stress. When that stress is being applied in this way, the force which is acting is given by only the second term, that is Fy. Now from this expression it automatically becomes clear that if we apply a stress in a particular direction, what is the direction in which the force will be acting on the dislocation, and that is the direction in which dislocation will move. So under the action of the external stress, if you apply a shear stress like this dislocation will move. If the stress which is applied is on the y surface in the z direction, now the dislocation will move in this direction or in this direction. This becomes very clear from this expression, but otherwise the qualitative way in which initially we started with, it does not become very clear. Now let us consider the another in the case of a edge dislocation, because so far we have considered for a screw dislocation. In the case of a edge dislocation, if we consider, we assume that we have a here. Okay. This is the coordinate system which we choose x, y and z. Okay. This is the u, and bias vector will be in this direction. Okay. If we apply any load to this cube, okay, we can find out the components of the stress which are going to be there and applied stress components in various shear as well as the with respect to a coordinate system. Okay. But as far as an edge dislocation is concerned, the only stresses which are present, internal stresses, are sigma xx, sigma yy, sigma zz and sigma xy. All other components are 0. So only these components can act on them. Then what is going to be the line direction u will be k into uz, because it's along the z direction. What is going to be the bias vector? Bias vector is I into bx, correct? Now let us derive an expression that these are all the stresses which are going to. Now what is going to be the pitch coherer force? If we look at this, now we will find that Gx will be equal to sigma xx into bx, because all other components, these components will turn out to be 0, correct? Gy will be equal to sigma yx into bx plus Gz will be equal to sigma zx into bx, correct? Sigma zx will not have any effect on the dislocation displacement. So this term is going to be 0. Now G will be I into Gx plus Gy dx plus J into sigma yx into bx, correct? Now we can take that what is the force which is going to act on the dislocation? That force is given by G cross U. Okay. Here again, if you take it, the cross product, I cross K will be, J cross K will be I, Yx into Bx into Uz minus J into Xx into Bx into Uz. Uz is the unit vector. So now we can see that this corresponds to Fx, okay. This term corresponds to minus Fi, correct. That means that if we apply a stress, assume that we are applying a stress which is only in the shear stress in xy direction, that is y plane in the x direction. That is what this represents. This introduces a stress. What is the direction in which this is on the positive direction? We apply sigma yx. Bias vector is in this direction. The force will be acting in this direction. This becomes obvious from this expression. Suppose we apply a tensile stress which is on this face, that is stress which is normal to this x surface, okay. Then the force which is going to act is, this is Fi. So you can immediately see that the force is in the y direction. That means that application of a tensile stress which we qualitatively, by looking at this demonstration, we try to understand it, this becomes obvious from this mathematical expression itself. Okay. This makes life much simpler because we can find out what direction stresses will be acting. So what we have to remember, only these expressions, okay, and that's all. This is all which we have to remember to calculate the force which is going to act on a dislocation. This force is very important. Unless we know the force, we will not be able to tell how the dislocation is going to move in a dislocation. Especially when the dislocation is a mixed dislocation, okay, the force will be acting on different directions on the dislocation. At every point, though the stress is applied in the same direction, but the effect of the stress on the dislocation, which acts in the form of a force, and it's a virtual force, as if a force is trying to push the dislocation, that force acts in a always perpendicular to the line direction. Is it clear? Okay. So far what we have considered is now essentially to derive an expression for the force which is acting on a dislocation, okay, and consider two cases wherein when external stress apply, what is the direction in which the force will be acting on the dislocation. The next case which will be considered is that when there are many dislocations are present, what are the types of forces which are going to act between the dislocations, okay, what sort of force which will be acting, force which will be acting depending upon the direction in which the dislocations are present. Okay, these dislocations could be, one could be an edge, one could be a screw dislocation. Okay, their directions could be different. This is what exactly which is required to know when we deform a sample. Okay, a lot of dislocations are generated, how they interact, their interaction will lead to whether a repulsive force or an attractive force. Depending upon that, the response of the material will change. These are all the aspects. For that, to understand how the material is going to respond, we should be able to find out the type of forces which act between dislocations. This we will take it in the next lecture. Okay.